sklearn. Calibration. Calibration display. Description. The calibration display class in Sci-kit Learn is a powerful tool for visually assessing the calibration of a probabilistic classifier. Calibration refers to how well the predicted probabilities from a model align with the observed frequencies of the target class. In essence, it evaluates whether the model's confidence in its predictions is justified. Inputs. CLF. This is the calibrated classifier object. It should be a fitted probabilistic classifier like logistic regression (SVC) with probability true, or a calibrated classifier from calibrated classifier CV. Why true? The true labels of the data. This input is typically an array of the actual target classes. Why PROB? The predicted probabilities of the positive class or any other class of interest generated by the classifier. This is usually an array of probabilities, with each element representing the probability of the corresponding data point belonging to the positive class. Name. A string that provides a name for the calibration display. This name helps identify the specific classifier when multiple calibration displays are plotted together. Strategy. This parameter specifies the calibration strategy used to calibrate the classifier. It can be sigmoid, isotonic, or none. Acts. An optional matplotlib axis object. If provided, the calibration display will be plotted on this axis. If not provided, a new axis object will be created. Quarks. Additional keyword arguments are passed to the underlying matplotlib plotting functions. Outputs. Calibration display. The calibration display object. This object is a representation of the calibration curve, including the predicted probabilities and the observed frequencies, and the visualization parameters. Acts. The matplotlib axis object containing the calibration plot. Steps. 1. Calibration. The calibration step involves transforming the raw predicted probabilities from the classifier into more calibrated probabilities. This is done using the specified calibration strategy sigmoid, isotonic, or none. Sigmoid. This method applies a sigmoid function to the raw probabilities, effectively rescaling them. Isotonic. This approach uses isotonic regression to find a monotonic relationship between the predicted probabilities and the observed frequencies. None. No calibration is performed. The raw predicted probabilities are used directly. 2. Visualization after calibration. The calibration display visualizes the relationship between the predicted probabilities and the observed frequencies using a calibration plot. This plot helps assess the calibration quality. Calibration curve. The calibration curve is the primary component of the display. It plots the predicted probabilities on the x-axis against the observed frequencies on the y-axis. A perfectly calibrated model would have a calibration curve that lies on the diagonal line, indicating a perfect match between predicted probabilities and observed frequencies. Confidence bands. The plot may include confidence bands to indicate the uncertainty in the calibration curve. Metrics. Reliability diagram. The calibration plot itself provides a visual representation of the calibration. Areas where the curve deviates significantly from the diagonal line indicate potential calibration issues. Calibration error. This metric quantifies the deviation of the calibration curve from the diagonal line. Commonly used metrics include expected calibration error is it measures the average difference between the predicted probabilities and the observed frequencies, weighted by the number of samples in each bin of the calibration plot. Maximum calibration error MCE. This metric captures the largest deviation between the predicted probabilities and the observed frequencies over all bins. Visualization plots. Calibration plot. The primary visualization is the calibration plot itself. It's a scatter plot or a line plot showing the predicted probabilities on the x-axis and observed frequencies on the y-axis. The ideal scenario is for the points to fall close to the diagonal line, indicating good calibration. Confidence bands. These bands are often added to the plot to show the uncertainty around the calibration curve. Fine-tune parameters. Strategy. This parameter controls the calibration strategy. Experiment with sigmoid, isotonic, and none to determine the best strategy for your model and data. NBINS. This parameter, usually found in the underlying calibrated classifier CV, determines the number of bins used for grouping the predicted probabilities. More bins can improve the visualization detail but might lead to less stable estimates. Method. This parameter, usually found in the underlying calibrated classifier CV, determines the method for estimating the calibration model for sigmoid strategy. Sigmoid generally offers good performance. Uncertainty methods. Confidence intervals. Confidence bands around the calibration curve provide visual estimates of uncertainty. Challenges and fixes. Challenge 1. Overfitting to the calibration data. When the calibration is performed on the same data used for training the model, the model might overfit to the calibration data, leading to optimistic calibration results that don't generalize well to new data. Sample use case that resulted in challenge 1. Calibrating a model with a small dataset and using the same data for both training and calibration might lead to overfitting. Fixes to challenge 1. Use a separate calibration dataset. Set aside a portion of the data specifically for calibration, distinct from the training data. Cross-validation. Employ cross-validation to estimate the calibration error more robustly by splitting the data into multiple folds, using different folds for training and calibration. Challenge 2. Insufficient data for calibration. If the dataset is relatively small, the calibration process might struggle to estimate accurate calibration parameters, leading to less reliable calibration. Sample use case that resulted in challenge 2. Calibrating a model on a dataset with a limited number of data points. Fixes to challenge 2. Increase the dataset size if possible. Collect more data to improve the robustness of the calibration. Use a simpler calibration strategy. Consider using a simpler strategy like sigmoid if the dataset size is small. Regularization. Utilize regularization techniques to prevent overfitting during the calibration process. Challenge 3. Poor initial model performance. If the underlying classifier is already poorly performing, calibration might not be able to significantly improve the predictive performance. Sample use case that resulted in challenge 3. A classifier that has a high bias or variance might lead to poorly calibrated predictions. Fixes to challenge 3. Improve the base model. Focus on enhancing the performance of the original classifier through feature engineering, hyperparameter tuning, or using a more suitable model. Calibration might not be the solution in some cases. Even with careful calibration, the model might not achieve good performance if the underlying classifier is fundamentally flawed. Sklearn mixture description. Explain in detail. Mixture models are a powerful statistical tool used for clustering and density estimation. They assume that the data is generated from a mixture of multiple probability distributions. The goal is to identify these underlying distributions and their respective proportions in the data. Scikit-learn's mixture module provides a set of algorithms for fitting mixture models to data. Inputs. Input 1. Explain in detail a data set of observations, typically represented as a 2D NumPy array. Each row corresponds to an observation, and each column represents a feature. Input 2. Explain in detail the number of components in the mixture model. This value specifies how many distinct probability distributions are used to model the data. Outputs. Output 1. Explain in detail a fitted mixture model object. This object contains information about the estimated parameters of each component distribution. Output 2. Explain in detail a set of cluster assignments for each observation in the dataset. This indicates which component distribution each observation is most likely to have been generated from. Steps. Step 1. Explain in detail initialization. The algorithm starts by initializing the parameters of each component distribution, such as mean, covariance matrix, and weights. Step 2. Explain in detail expectation maximization. M algorithm. The M algorithm iteratively refines the parameters of the mixture model until convergence. In the A step, the algorithm calculates the probability of each observation belonging to each component distribution. In the M step, the algorithm updates the parameters of each component distribution based on the calculated probabilities. Metrics. Metric 1. Explain in detail एक AKK information criterion. A metric that balances model fit with model complexity. Lower AKE scores indicate a better model. Metric 2. Explain in detail big Bayesian information criterion. Another metric that balances model fit with complexity, often penalizing more complex models than AKE. Lower big scores indicate a better model. Visualization plots. Visualization plot 1. Explain in detail scatter plot used to visualize the clusters identified by the mixture model. Each point represents an observation, and points are colored based on their assigned cluster. Visualization plot 2. Explain in detail density contour plot used to visualize the probability density function of the fitted mixture model. This plot shows areas of high and low probability in the feature space. Fine-tune parameters. Parameter 1. Explain in detail n components. The number of components in the mixture model. Increasing this value allows for more complex models but can lead to overfitting. Parameter 2. Explain in detail covariance type. Specifies the type of covariance matrix used for each component distribution. Options include full, tied, diag, and spherical, each impacting the shape and complexity of the distributions. Uncertainty methods. Uncertainty method 1. Explain in detail predictive entropy. Measures the uncertainty associated with predicting a new observations cluster assignment. Higher entropy indicates more uncertainty. Uncertainty method 2. Explain in detail Bayesian inference can be used to estimate the uncertainty in the estimated model parameters. Challenges and fixes. Challenge 1. Explain in detail overfitting. If the number of components is too high or the model is too flexible, it can overfit the training data and fail to generalize well to new data. Sample use case that resulted in challenge 1. A dataset with 100 samples and 5 features is fit with a mixture model with 10 components. The model perfectly fits the training data but performs poorly on unseen data. Fixes to challenge 1. Reduce the number of components. Use regularization techniques, e.g., L1 or L2 penalties. Or use cross-validation to evaluate model performance on unseen data. Challenge 2. Explain in detail initialization sensitivity. The M algorithm can be sensitive to The initial parameter values. If the initialization is poor, the algorithm may converge to a suboptimal solution. Sample use case that resulted in challenge 2. A mixture model is initialized with random parameters, and the M algorithm converges to a local minimum instead of the global minimum. Fixes to challenge 2: use multiple random initializations and select the model with the best performance, or use a more robust initialization strategy, such as k-means clustering. sklearn, mixture, Bayesian Gaussian mixture. Description: a probabilistic model that assumes the data is generated by a mixture of Gaussian distributions, with the number of components learned automatically. It utilizes a Bayesian approach with a Dirichlet process prior for the number of components, allowing for flexible model selection. Inputs: X, a 2D array of shape n samples. N features, representing the data points. N components, an integer specifying the maximum number of components to consider. The model will automatically determine the optimal number of components within this range based on the data. Outputs: weights, a 1D array of shape n components, representing the mixing weights for each component. Means, a 2D array of shape n components. N features, representing the mean vectors for each component. Covariances, a 3D array of shape n components. N features, representing the covariance matrices for each component. Steps: initialization: the model initializes with a random number of components within the specified range. Expectation maximization: EM algorithm: the model iteratively alternates between the following steps. A step calculates the posterior probabilities of each data point belonging to each component. M step updates the model parameters, weights, means, and covariances to maximize the likelihood of the data given the current component assignments. Bayesian inference: the model uses a Dirichlet process prior to regularize the number of components, preventing overfitting. The prior encourages sparsity in the model, effectively selecting the optimal number of components. Metrics: Bayesian information criterion: Bickel score used to select the best model based on the trade-off between model complexity and data fit. Akeke information criterion: another score similar to BIC, used for model selection. Visualization plots: scatter plot: visualize the data points colored by their assigned components, highlighting the clustering structure. Density contour plot: overlay the density contours of each component on the scatter plot to visualize the distribution of data within each cluster. Fine-tune parameters: n components, the maximum number of components to consider. Weight concentration: prior type controls the strength of the prior on the mixing weights, influencing the sparsity of the model. Options include Dirichlet process and Dirichlet distribution. Weight concentration: prior, a float specifying the concentration parameter for the Dirichlet prior. Uncertainty methods: predictive distribution: the model can provide uncertainty estimates for new data points by calculating the predictive distribution, which represents the weighted average of the component distributions. Confidence intervals: the model can calculate confidence intervals for the estimated parameters, providing a measure of uncertainty. Challenges and fixes: Challenge 1: choosing the right number of components. Sample use case that resulted in challenge 1: a data set with a complex underlying structure that may require a large number of components, but overfitting could occur if the number is too high. Fixes to challenge 1: use the BIC or AIC score to guide the selection of the optimal number of components. Explore a range of possible values for n components and compare the model performance using cross-validation. Challenge 2, dealing with high-dimensional data. Sample use case that resulted in Challenge 2, a data set with many features, which can lead to computational difficulties and potential overfitting. Fixes to Challenge 2. Use dimensionality reduction techniques such as principal component analysis (PCA) or feature selection methods to reduce the number of features. Consider using a more efficient algorithm for fitting the model, such as the variational Bayes method. Challenge 3, handling data with different scales. Sample use case that resulted in Challenge 3, a data set with features having vastly different ranges, which can negatively affect the model's performance. Fixes to Challenge 3. Standardize or normalize the data to ensure that all features have a similar scale. Experiment with different covariance structures to accommodate the potential differences in feature scales. sklearn. Mixture. Gaussian mixture. Description. Gaussian mixture is a generative probabilistic model used for clustering data. It assumes that the data points are generated from a mixture of Gaussian distributions, where each Gaussian represents a cluster. The model learns the parameters of each Gaussian mean, covariance, and mixing proportions to best fit the data. Inputs. X, a 2D array of data points, where each row represents a data point and each column represents a feature. N components, the number of Gaussian components in the mixture model. This value is specified by the user based on prior knowledge or by trying different values to find the optimal number of components. Outputs. Weights, a 1D array of mixing proportions for each Gaussian component. These values represent the probability of a data point being generated from a specific Gaussian component. Means, a 2D array of mean vectors for each Gaussian component. Each row corresponds to the mean vector of a specific component. Covariances, a list of covariance matrices for each Gaussian component. The covariance matrix describes the spread and orientation of the Gaussian distribution in P. Feature space. Predict probx returns the probability of each data point belonging to each component. This is useful for understanding the likelihood of a data point belonging to a specific cluster. Steps. Initialization. The algorithm starts by randomly initializing the parameters of the Gaussian components. Expectation step. The algorithm calculates the probability of each data point belonging to each Gaussian component, based on the current parameters. These probabilities are known as responsibilities. Maximization step. The algorithm updates the parameters of each Gaussian component based on the responsibilities calculated in the expectation step. Repeat. The expectation and maximization steps are repeated until convergence, meaning the parameters no longer change significantly. Metrics. AIC information criterion, a metric that balances the model's goodness of fit with the complexity of the model. Lower AIC values generally indicate a better model. Big Bayesian information criterion, similar to AIC but penalizes model complexity more heavily. Lower big values generally indicate a better model. Log likelihood measures the model's ability to fit the data. Higher log likelihood values generally indicate a better model. Visualization plots. Scatter plots can be used to visualize the data points colored according to their cluster. Assignments. Contour plots can be used to visualize the density of the Gaussian components. Pair plots can be used to visualize the relationships between features within each cluster. Fine-tune parameters. N components, the number of Gaussian components in the mixture model. Covariance type: the type of covariance matrix to use for each Gaussian component. Can be full, tied, diag, or spherical. Told: the tolerance for the stopping criterion of the M algorithm. Maxiter: the maximum number of iterations for the EM algorithm. Random state: the random seed for initializing the model. Uncertainty methods. Predictive uncertainty can be estimated by using the probability of each data point belonging to each component. Model uncertainty can be estimated by fitting the model multiple times with different initializations and comparing the results. Challenges and fixes. Challenge 1: choosing the optimal number of components. Sample use case: if the number of components is too low, the model may not capture the true structure of the data. If the number of components is too high, the model may overfit the data. Fixes to challenge 1. Use metrics like AIC and BIC to compare models with different numbers of components. Perform cross-validation to evaluate the model's performance on unseen data. Challenge 2: handling high-dimensional data. Sample use case: if the data has many features, the covariance matrices of the Gaussian components can become very large and difficult to estimate accurately. Fixes to challenge 2. Use dimensionality reduction techniques like PCA to reduce the number of features. Use covariance types like tied or diag that constrain the covariance matrices to have fewer parameters. Challenge 3: dealing with outliers. Sample use case: outliers can significantly influence the parameter estimates of the Gaussian components, leading to a poor model fit. Fixes to challenge 3. Use robust estimators for the mean and covariance of the Gaussian components. Remove outliers from the data before fitting the model.